let's talk about this. So here we have, we're talking about the four fundamental forces. So in physics right now, we believe that there are four fundamental forces. So going from weakest to strongest, that would be gravity is the weakest. Then the weak nuclear force. So most of you guys know what gravity is responsible for. Then there's the weak nuclear force, which is essentially what causes the nucleus of an atom to split. We call that radioactivity. So, you know, you can think of like the weak nuclear force kind of responsible for atomic bombs. And then you have the electromagnetic force, which is, you know, obviously electricity and magnetism, allows electrons to orbit around the nucleus. And then you have the strong nuclear force, which holds the protons and neutrons together inside the nucleus. So you look at this video here, it gives you a little bit more of a description on that, about the four fundamental forces and how they're kind of interacting with each other. In this section, we're obviously going to focus on the strong nuclear and the weak nuclear. Here is the standard model. With the standard model, we have all of these parts. Standard model is by no means complete, and it's by no means pretty. I know this picture looks pretty, but it's not really that pretty when you start to look at the theory. The important parts of this chart, you know, like I said, you can click on this and go through to a website where you can interact with these things a little bit more. There's essentially four parts of this chart. We got quarks, leptons, then we have our force carriers, and then the Higgs boson. And so the Higgs boson, we believe that, you know, when you go from energy to matter, the Higgs boson is the first thing that's formed out of this, you know, energy. Basically, you get enough energy in one spot for whatever reason. Then the Higgs boson is formed, and as it decays, it creates other things like electrons and protons and all that. So you'll notice the electron is right here on our chart. It's, you know, one of our leptons. I'm not going to get, like I said, into too much detail here. This will make a little bit more sense as we go through some things and you see different reactions. And you're like, oh yeah, I remember it saying that that thing existed. But most of this standard model we're not going to hit on. I mean, electrons are obviously important. And you might notice you don't see the protons or neutrons on here because they're composed of some of these quarks. So protons are two up quarks and a down quark, and neutrons are two down quarks and an up quark. So again, we found that when we can get enough energy together, we can split protons and neutrons, and that's how we know it's inside of them. And basically, the other things, you know, you look at the electron with the muon and the tau, they're essentially just like, almost like heavy electrons. And so you can kind of think of something similar with like the up quark and the top quark and stuff like that. I'm not going to get too deep into this because we're not really testing over any of that, but I want you guys to kind of be able to see what we know. So, how is this related to anything? So first of all, we're talking about protons, neutrons, and electrons for the most part. And you need to know what's inside of those guys. So inside your protons, we get two ups and a down. Neutrons got two downs and an up. And you can see here that, you know, we say a proton or neutron has like a fundamental amount of charge. We call it the elementary charge. We called it elementary because we thought, you know, you can't split that apart. But at least for protons and neutrons you can. It doesn't seem like we can split apart electrons. Maybe one day we'll be able to do that. Or maybe you can't. So here, you'll notice that the up quarks are written as 2/3 of your elementary charge, and then down quarks are written as -1/3. And so, you know, if you do that math, you can see why protons would have 1 for your elementary charge, and neutrons would have neutral elementary charge. And so this is basically what you need for the atom, but you know, as we go through some of these other nuclear processes, you'll see some things like definitely you'll see a couple of neutrinos now and then, and obviously like the photons are going to come back. But Just basically, when I get to talking about some of these other pieces, I don't want you just going, oh, where did this stuff come from? So that's kind of why I want to start with a standard model. Are there any questions so far? I'm going kind of fast, so. All right, so this, this section is so weird. So you'll notice that this is titled antimatter. So first of all, yes, antimatter is real. And you probably heard of it from, science fiction or whatever, or, some books and stuff. And it's in pop culture, like Star Trek. That's how their ships are supposed to work. They're supposed to work based on a warp drive. And the way a warp drive works is it literally warps the fabric of space and time. And essentially, the ship would ride this ripple, this wave in the fabric of space-time, just like a surfer would ride a wave on the ocean. And so that's why it's called a warp drive, because it warps the fabric of reality, which is kind of weird to think about. But in Star Trek, that warp drive is powered by antimatter. And essentially, antimatter is very similar to actual matter, except the complete opposite. So it says every subatomic particle discovered has an antiparticle twin that has the same mass, so exact same mass, and with the same, we say spin, but spin is like, think of it like the magnetic part of the particle. It's not, sort of, I'm not going to get more into that. But it's going to have an opposite charge. So for example, if you look at the electron, it has an antiparticle twin, which has the exact same mass as the electron. It would have the same spin when it was created with the electron, and it would have not a negative charge, but a positive charge. Most antimatter is just called anti-whatever, like an anti-proton is called, well, an anti-proton, right? The anti-electron, you can call it anti-electron, it does have a special name, it's called a positron. So there are positrons, anti-electrons, anti-protons, anti-neutrons. The anti-neutron is still neutral, but not the same as regular. I'm not going to jump into that. You can just basically think of it having different quarks inside of it. And antimatter versions of all of the various subatomic particles. So that standard model I just showed you, basically every single one of those things, I don't know if all of them, but basically all of them, we've seen an antimatter version of it. So like that standard model I showed you is essentially half of our fundamental particles. So when a particle and its antiparticle meet, the two annihilate, leaving nothing but energy behind. So if you have an electron and a positron and they touch, well, they turn into pure energy, which is why, like, a lot of science fiction shows use antimatter, because you don't need much of it to create a lot of energy, right? For example, I talked about the atomic bomb on Hiroshima. That particular bomb destroyed pretty much the whole city. And if we're looking at just E equals mc squared, the amount of matter that was actually converted to energy was only about 1 kilogram. So 1 kilogram was enough to destroy a whole city. Now the bomb was obviously bigger than that. They needed other things to like make the explosion occur, but essentially only about 1 kilogram of matter was actually converted in that explosion. And so when you realize like that was basically just 1 kilogram, there's a lot of energy that could come out of E equals mc squared. So here's the deal. Whenever they collide, they create energy. You can think of pretty much all of it coming out as photons. And the energy a photon has will be directly related to its frequency. And so lower energy things like radio waves and microwaves, they just don't have that much energy. So a larger thing that annihilates, like like an electron and a positron annihilating each other, are going to give off huge amounts of energy. So this is going to be more like gamma rays in terms of their frequency. So very high frequency, very large amounts of energies for these photons. And sometimes it creates other particles. It kind of depends on what annihilates and how it annihilates. We're not going to get into too much of that. I want you guys to know this, again, this stuff exists. Because again, when we go through some of these nuclear reactions that we're going to look at, like weird stuff starts popping out. So first of all, antimatter is real. We've created it in a lab. So we've definitely done the turning matter to energy part. I think most people know about that one. But a lot of people don't realize that we've gone the other direction as well. We've taken energy and created matter. And whenever that happens, if we create matter from energy, all of our conservation laws are still hold. And so if you realize that energy and matter are just two sides of the same coin, well, it's not being created or destroyed. You're just getting enough energy together to make it into a different form, right? You can have kinetic energy turn to gravitational potential. You can have it turn into mass as well. But also, like, the laws of like charge still hold. So like if you create an electron, well, it doesn't pop into existence by itself. You also create a positron. And so you have a positive and a negative, so charge is still balanced. And when we do this, we typically do it inside of a vacuum chamber with a very strong magnetic field so that we can cause the two, let's say electron and positron, to spin apart from each other. And we've been able to create it, I think it was last year, they were able to create this stuff, and they have to hold it in a strong electromagnetic field, because again, if you're, the electron, you can just let that go, it'll be fine. But like the positron or antiprotons or whatever, you can't let them touch anything, because if they touch anything, they'll annihilate and turn back into energy. And so it's kind of funny because, like, if you think about it, like, okay, we can create it, where are you going to keep it? You're going to stick it in a jar? Well, the jar is made out of matter, so if it touches the wall, it's going to annihilate and turn back into energy, and it'll just explode. So it's very difficult. Like, we can create it, but usually not for very long. But I think it was last year, either last year or the year before, they were actually able to do something incredible. They were able to make antiprotons, literally put them in a van and drive them across the parking lot to do a different experiment, because essentially they had an experiment over here that they wanted to do, and they were like, well, we can make antiprotons over here, but we got to get them across, like literally it was like 50 feet across the parking lot. But they had to build like this whole thing, because that's not, you can't just, like you can't just put it in a jar. And so what's funny is that there's a movie and a book, called like Angels and Demons or something like that, like the Da Vinci Code. Da Vinci Code, that's the first one. In the Da Vinci Code, like one of the very first things that happens is that somebody breaks into CERN, like the Large Hadron Collider, where they make antimatter, and they steal like a jar of antimatter. I'm like, what? Just pick that up, like, because the guy's like chasing them down, like, oh no, they stole it. Like, I'm like, wait, what? Like somebody just breaks it and just puts it in their pocket, like. I'm like, I can't. It was, I mean, I get science fiction, but that's where I stopped paying attention to the movie, which is like one of the very first things that happens. And I'm just like, I can't. I get it, movies and books, they involve some suspension of disbelief, but that was too much for me. I was like, no, I'll believe Thanos, but this is too far. So. Because, at least, when the other people make it up, they're like, oh, it has some, like on Star Trek, it's like held in some weird crystal thing. I'm like, okay, fine. I'll buy that. But it was just like a jar, like, oh, somebody took it. Here, this link here for a particle collider, I believe, I'm not going to play it, just double checking. Yes, I would watch this. I'm not going to play this in class. This is a video animation actually from, here's the Science and Technology Facilities Council. This is, it's basically the Large Hadron Collider and how it actually works. So essentially, you start with some hydrogen and how they get them up to speed there. So I'm not going to go through all that here in the notes. Maybe if we have time later, I can play it. But I encourage you to look at that. It kind of talks about how the Super Collider actually gets these things going up close to the speed of light. So they can do it with pretty much any particle that has a charge. So they usually use protons, but sometimes antiprotons or whatever. So I want to say that because, again, when we look at these reactions, you're going to see like a positron. You're like, wait, hang on, what is that? So there's different models of the atom. And so over time, at first when they discovered the atom, they thought that was a truly fundamental thing that was solid, nothing could be broken apart from it. But we've obviously evolved here. And so hopefully you remember some of the stuff from chemistry that, like in chemistry, historically speaking, they started with like the billiard ball view that's just a solid chunk, right? It's just an atom, right? And then we realized like it's not exactly that, and they started, Rutherford started like his gold foil experiment where he was like shooting electrons, not electrons, but shooting something, electrons and neutrons, I can't remember, at atoms, and then he noticed that most of them would just go straight through, but then some would bounce off, and that led to like the plum pudding model that's it's mostly empty, but there seems to be something solid in it. And then here, the classical solar system model, where you just have like a positive thing in the middle and electron just orbiting it because it orbits just like a planet orbits the sun because of gravity. And I feel like that's where most people's thoughts stop, even though I know personally for me, I was introduced to the Bohr model definitely in chemistry, but my thoughts never actually got past the solar system model. Now the Bohr model is different than the solar system model. They look very similar, but the Bohr model, remember, is different because there was very specific places that your electron could be. Whereas with the solar system model, like planets can just be anywhere. They just happen to be where they are because of whatever they formed. But literally you can have anything anywhere in the solar system. But like the Bohr model, the specific difference here is that it has very specific places that electrons can be, right? That's why you guys learned it. Now, we know the billiard ball model is wrong. We know the plum pudding model is wrong. We know the solar system model is wrong. We know the Bohr model is wrong, okay? What you guys should know from chemistry is the reason why we still use the Bohr model and still teach it isn't because we like lying to you. It's because it's the easiest model. Like after that, it gets weird. It's the easiest that you can still conceptualize in your mind without getting too mad, essentially. But we know the Bohr model is wrong, okay? And then came the Broglie model, which is based, it's very similar to Bohr, and then now we're to the Schrodinger model. And you guys, I'm sure, have seen all of these, especially if you took AB Chem. The de Broglie model, the main difference between that and the Bohr model is it's not just, it's saying, okay, well, why? Because first of all, the Bohr model only works for the hydrogen atom. That's it. It doesn't work for anything else. I mean, you could think of other things like that, but they're all wrong. That's how we know Bohr model doesn't work. Like it works for hydrogen, but not helium. So that's a pretty bad failure if you can't get to number 2. The de Broglie model basically started thinking of electrons as waves. And if you think about like a string, you could have, like if you think about strings in a guitar, you can have these strings of a certain length or whatever, it depends on your guitar, but when you pluck the string, it'll have a wave on it. And the wave can only be of a certain length to be on the string. Does that make sense? If the wave is too long, the string can't make that wave. Which I'm not talking about like touching them or changing the length of the string. I mean, just saying you just have a length of string. If you pluck it, it'll have a frequency it'll vibrate at. You can make it vibrate faster or slower, but it's only certain multiples of that fundamental that it can make. And that's what the de Broglie is talking about. Is like if you look at the Bohr model, it's like, okay, well, why these specific rings? Why these specific spots? And it's because if you think of the electron as a wave, well, it can only make like a complete, full wave cycle at these points. And what points they are, well, there's a lot of things that go into that. Because it's honestly, it has everything to do with, how many electrons, electrons are in the orbits, but also the neutrons and protons in the nucleus itself. Like they all affect each other. So there's so many different things. But what's really interesting about all of this is you start to realize, like, okay, well, if I put like one more neutron in there, it affects everything about that atom. It seems pretty infinite. It seems kind of like the solar system. We can just do it wherever, but it's not. And that's what's very interesting is that these frequencies are very specific. So like if you have this certain setup, it has this very specific, frequency associated with it. It's not random. And then we have the Schrödinger model, which is more like a three-dimensional viewpoint, because basically up until the Bohr model, everything was pretty much like thinking about it in 2D, but everything's everywhere. And the Schrödinger model is where you get like those S and P orbitals. Like I don't know. I mean, that's not where they come from, but like you remember, like you were talking about, like the S orbital is essentially like a sphere, and then like the P is like some weird like teardrop thing or whatever. Like that is predicted by the Schrödinger equation. And so when I say Schrödinger model, you've probably seen it, but it's all the weird like cones and all these weird like because essentially it's not a. It's kind of like this, but it's just like a region of probability, right? It's not like it's actually there. We just think, it's like 95% chance it's in this general vicinity here most of the time. And so these are the models that we've gone through. The Schrödinger is by far the most accurate that we know of, but it's going to be one of the hardest to understand. And especially if you went through chemistry and you saw like these different models and you had to be tested on it, that's even without the math, that's still kind of difficult. Because I remember like having to be tested on like the different shapes and be like, oh, that's kind of a pyramid looking thing, But that's not what my teacher wanted. So again, Bohr model was developed to meet problems caused by the theory that electrons have discrete energy levels. So that's where the Bohr model came from. It was fixed by the realization that particles can act like a wave. But again, it's outdated, but we still use it to visualize atoms for most people. Because you can kind of explain this to most people. So again, why do we still use this? The electrons in free atoms can only be found in certain discrete energy states. These sharp energy states are associated with orbits or shells of the electrons, i.e. a hydrogen atom. One of the implications of these quantized energy states is that only certain photon energies are allowed when electrons jump from higher to lower levels, producing the hydrogen spectrum. The Bohr model successfully predicted the energies for the hydrogen atom, but only the hydrogen atom. So okay, let me take a step back here. So here we think about hydrogen, the simplest atom we know of. We just got a proton, and let's say we just have one electron orbiting it. That electron would want to orbit down here on this blue path, right? The lowest energy level. And if you have a photon, like a chunk of electromagnetic energy come in, this electron here could absorb it, but it can only absorb it at particular frequencies. If it's the right frequency, it could, when I say frequency, also think of energy. If it's the right energy, it could cause it to jump from this orbital to that, to the second one. Or if it's, let's say 3 times that energy, maybe it jumps up to the third one. Maybe like 8 times that energy, it jumps up to this fourth one. But here's the deal, does this electron want to stay out here in this outer orbital? No, it wants to go back down there. And so what it does, let's say it jumps all the way out here, okay? When it falls down, does it have to fall all the way down? No, it could fall down to any one of these other levels. And so let's say one chunk of energy, one photon comes in, and it jumps it all the way out here to, let's say, this 4th energy level. Okay, well, it's out there, it's spinning around. Let's say it falls down to the 3rd one. Well, then it'll release some of the energy, but not all of it. Then maybe it spends some time at the 3rd level, then it falls down to the 2nd, releases a bit more, and then releases a bit more when it comes down. So what's interesting is that you could have, let's say, one photon come in and makes it jump up to the 4th level, but maybe 1, 2, 3 photons come out when it falls back down. And so this is essentially the easiest example of something like this is actually why the sky is blue. when light comes in from the sun, it hits our atmosphere. And our atmosphere is mostly nitrogen and oxygen. A lot of those frequencies, like the lower energy ones, like the yellows and the reds, are not the correct frequency to cause the electrons of nitrogen and oxygen to jump up to higher energy levels. The ones that are of the right frequencies are the blues and actually the violets. The violets are the ones that are absorbed the most. But here's the deal. If they're not absorbed, like if a photon comes by and it's not the right frequency, well, it just passes on by. It just won't interact. But if it's the right frequency, then it'll cause it to jump up to one of these energy levels. Now, it could cause it to jump all the way up, maybe just jump up a little bit. It depends on the frequency of the wave. But that is really strongly interacted with the violets and the blues. And so what happens is the nitrogen and oxygen in the sky will absorb those photons, those packets of energy for a minute, and then they will release them. But here's the deal. When it releases the energy, when the electron falls back down, does it have a reason to send it in any particular direction? No. And that's where we get the scattering from. So essentially, if you look up at the sky, if the sky was blue right now, if you look up at the sky, let's say the sun is, in point A, well, you look at a patch of sky over here, to the left of it or whatever, that looks blue because light came from the sun, hit this patch of sky, got absorbed, and then got scattered, and you're seeing the light coming from your eyes. So it's like basically going from the sun, hitting that patch of sky over there, and being scattered to your eyes so you can see it. Now, I say it's actually the violet light that scattered the most. And so the real question isn't why is the sky blue, but why is the sky not violet? And the reason for that is our eyes are actually really bad at seeing violet. I mean, we'll see it basically if there's nothing else in the way, but there's actually more violet light being scattered to your eye than blue. Just the blue has, we absorb that easier, or our eyeballs do, and so that's basically why we see that.
I thought things were a certain color they didn't absorb it. Like they absorb everything except for that color.
Yes.
Because
it didn't, okay, but here's the deal. You're thinking of like a shirt. Like if my shirt was orange, you're seeing orange because it's absorbed everything else and reflecting orange. That's true. The sky absorbs that color, but then it also re-emits it. Whereas your shirt doesn't absorb orange and then re-emit it. It just doesn't absorb the orange. And so like your shirt is different because when it absorbs, let's say like the blue, it doesn't re-emit that. Your shirt gets warmer because it's absorbed the blue. There are frequencies of light that do that as well, for the sky, but they're not visible frequencies. Basically, you can measure all of the visible light coming from the sun in space and on Earth, and if you account for the random scattering, it's all there. The atmosphere absorbs a little bit of infrared and a little bit of microwave, but it absorbs mostly the higher energy stuff, like the X-rays and the gamma rays, and the ultraviolet. So that's the stuff that absorbs, so everything else is basically passing through, but it's also scattering it. And so your shirt also would scatter it, like my shirt scatters like an orange light. Like if I just stand underneath the light, you see orange not just because it absorbs the other colors and reflects orange, but also because like the light hits me and scatters in all directions. Like it doesn't reflect like a mirror, right? And so there's two things happening. Does that help a little bit? Yeah. Okay. So, and that's actually that attitude right there is why a lot of people say the sky is blue because it scatters the light. But like almost nobody says that the water is blue because the water is blue or cyan or blue, green, whatever you want to call it. Because it doesn't absorb anything. And again, you're still just seeing a scattering effect. But water is a little different because it absorbs the red, leaving the blues and greens. And so you can say, okay, that is blue, green, or cyan, or whatever you want to call it, because it absorbs red, reflects the rest. Okay, I get that. But if you've ever scuba dived, you'll notice that as you go lower, it just absorbs more light until you get to the point where it absorbs all of it. So what's really fun about water is if you have a bathtub, like a white bathtub, try this sometime. I know it's been a while since y'all took a bath, but if you plug the drain and just turn on the water, just watch it. You can have it in your sink too, but it's easiest to see with the bathtub because of the volume. Just watch the water, it'll be clear until there's nothing. And then you'll notice there's a slight blue tint to it. Because again, it's enough to absorb enough of that red light that you start to see just the cyan come through. And if it's not cyan, then there's something else in the water. Okay? I'm saying there's a reason why Lake Louisville is not nice cyan color. So here this talks about the spectral lines. We'll talk more about that when we get to light. I have the periodic table of spectra over there. And essentially that's just for visible light. But again, when these electrons absorb light and then re-emit it, it's at very specific frequencies. So specific that the spectra of light, like this atomic spectra, has been likened to like a fingerprint for atoms. And the theory goes that fingerprints are 100% unique and can identify individual people. Well, the atomic spectra is 100% unique and can identify individual atoms. So fun fact, hydrogen was actually first discovered on the sun, second discovered on the Earth. We knew hydrogen existed because we looked at the light coming off of the sun and we could pick out all of the individual elements and we were like, huh, what is this thing? We call it hydrogen. And then later on we found hydrogen deposits here on Earth. So we actually named it after the sun. Which is interesting to think about, that we discovered something in a place that nobody's ever been. But that's how astronomy works. Is that the end of this? Okay, cool. I believe that's the end. All right, so that's just kind of like a nice intro here.